Welcome, my name is Andrea Campagner, and today we will be presenting our paper published together with Davide Ciucci titled A Formal Learning Theory of Three-Way Clustering. First, I will briefly describe the notion of clustering, which is an unsupervised learning approach whose goal is finding either patterns in datasets. There exist many clustering algorithms, for example, hierarchical approaches, partitive approaches, or spectral methods, density-based methods, and so on. An interesting question is whether we can assess somehow the theoretical properties and compare the formalisms underlying these approaches. In the case of supervised learning, these issues have been widely studied under the frame of computational or statistical learning theory. Typical properties of interest in this context are the expressivity of an hypothesis class, which is often called model capacity and is measured through notions such as the Vapnik-Chervonenkis dimension, or otherwise stability notions, which measure the robustness of these models when we make small changes to the training set. However, the study of similar concepts for clustering is less well developed. A recent approach towards toward this goal proposed by Klemberg is based on an axiomatic approach. Namely, there is a proposal of three axioms that characterize some intuitively good properties of a clustering algorithm. The basic ingredients in this formulation are a distance function, which is not necessarily a metric, because it is not required that these functions satisfy the triangular inequality. And then we have that a clustering algorithm is simply a function mapping a space together with the distance function to two partitions of the input space. The three axioms defined by Klemberg are, the first one is called richness, and essentially is a model capacity axiom. The idea is that a clustering algorithm is rich if it, at least in principle, is able to identify the correct partition. So the image of the clustering algorithm is the set of all partitions. The second axiom is called scale invariance, and it means that when we zoom in or zoom out, that is, we change the scale of the input space uniformly, then the result of the clustering algorithm does not change. This is essentially a stability requirement. And finally, the last axiom, which can also be seen as a stability, as a condition characterizing stability, is called consistency. The definition of this property is a bit more technical and is reported in the formula that you can see on the right. And basically, it can be described in an intuitive way by saying that consistent variations of the input space do not alter the result of a clustering algorithm. The main result of the paper by Klemberg is that there are no clustering algorithms satisfying all three properties. This is essentially a no-free lunch theorem because it negates the possibility of a universal clustering algorithm. But another interesting aspect of this theorem is that if we forget one of the axioms, then there exists a variation of single linkage, which is one of the most basic clustering algorithms that satisfies the two remaining axioms. There have been many other works that have extended this basic framework. For example, for finding theoretical characterization of quality measures for clustering, or that have studied some relaxation of the axioms. For example, by restricting the number of clusters. And so in this case, for example, we speak of K richness, or by proposing different consistency definitions. Usually the scale invariance axioms is not touched as it is usually a good property. The limitation of all these approaches and studies is that they can only be applied to hard clustering. However, many clustering approaches used in practice are usually soft, in the sense that the assignment of instances to clusters is not clear-cut. For example, we can have probabilistic clustering, fuzzy clustering, or also three-way clustering, which will be the main focus of the paper and of the presentation. What is three-way clustering? It is a simple generalization of standard hard clustering in which each cluster is represented as a pair, in which we have a core region, which contains the elements that certainly belong to the cluster, and the boundary or fringe region, which represent the objects that we are uncertain about and that they may belong to the cluster. Many similar or also equivalent formulas have been studied that use these type of structures. For example, rough clustering, interval set clustering, ortho partitions, or also some specific families of partitions. If we want to study the theoretical properties of three-way clustering, then the first step should be providing a meaningful generalization of the axioms that I've described before. The most natural candidate for generalization is richness, because one of them, the other two axioms are still natural in the context of three-way clustering, while maybe the richness condition it is not, because we have generalized to a wider family of possible clustering structures. So a first tentative generalization of this property is what we call three-way richness, in which we simply require that the image of our clustering algorithm is the set of all three-way clusterings. As a simple corollary of Kleinberg results, however, we can prove that no three-way clustering satisfies consistency, scale invariance, and three-way richness. Is this really a limitation? Well, our argument is that it is not. In fact, the question that we can pose is whether the notion of three-way richness is really meaningful. To grasp this idea, we should get at the intuitive meaning of richness, which means that at least in principle, we can find the appropriate partitioning if we are given a, let's say, noise-free distance function. In the context of three-way clustering, however, the instances in the boundary have a different status and meaning from the instances in the coregion. In fact, they do not represent, they represent somehow approximated assignment and our degree of uncertainty. What we are interested in is still recovering the partitions and not the three-way clusterings. So we proposed a different generalization of richness that we called almost richness, and it is based on two conditions. The first condition is a very weak condition, and we simply require that if we take all possible three-way clustering given by our algorithm, and we take all partitions that are compatible with this three-way clustering, then we get the set of all partitions. As I said, this first condition is very weak, as there is a very simple three-way clustering algorithm that satisfies it, which namely is the algorithm that always returns a single cluster in which all objects are in the boundary. Obviously, this algorithm is not useful at all. So we added another condition. This condition says that for every non-trivial clustering, I will explain what non-trivial means in a bit, there exists a corresponding and appropriate distance function. This is essentially equivalent to the original richness axiom, however we restrict it to the case of non-trivial clusterings. Which are the non-trivial clustering? Well, there are two trivial clusterings, and all other ones are non-trivial. The trivial clusterings are the clustering in which we have a cluster for each instance, and the clustering in which we have a single cluster that contains all instances. They are trivial because they are very strange structures that we do not expect to discover in the reality. So we get at the main result of our paper, which is the following theorem. The fact that there exists a three-way clustering algorithm that satisfies consistency, scale invariance, and almost richness. Intuitively, this is similar to the notion of representation-independent learning. While we have the no-free-lunch theorem for standard clustering, here by using three-way clustering we get a more general representation and more flexibility. However, this is still surprising because in the case of supervised learning, even if we use representation-independent learning, the no-free-lunch theorem um, holds regardless of this fact. While the consequence of this result is that in the case of clustering, by going to representation-independent learning, the no-free-lunch theorem do not hold anymore. So we give a bit of a proof sketch for our construction. In fact, the proof that we make in the paper is constructive, by which I mean that we propose actually an algorithm that satisfies these properties. We start from two very natural quality metrics, one which measures the in-cluster similarity and that we would like to maximize. So we would like to minimize the distance among instances that belong to the same cluster, while the second quality matrix measures the inter-cluster variance, and we would like to maximize this second matrix, which intuitively measures, quantifies the fact that instances that belong to different clusters on average should have a large distance. Then we define a quality partial order over clusterings, which is essentially a version of domination since we have a multi-criteria optimization problem. The result of the algorithm is the most specific three-way clustering, which is consistent with all non-dominated clustering. What this means? This means that essentially when we have a three-way clustering, we have some objects in the boundaries, and each assignment of the objects in the boundaries to the corresponding clusters leads us to a hard clustering, or equivalently a partition that is consistent with the original three-way clustering. So the result of this algorithm goes the other way around. You can see a listing of this algorithm in pseudocode on the right. As you can see, it is very simple. It is basically two nested fors. However, it is very computationally complex because we have to enumerate all possible partitions. So the complexity is super exponential. So going forward with the proof sketch, scaling variance and consistency are quite trivial because the algorithms does not use fixed scale points, and so we will not focus on the case of scaling variance and consequence and consistency, but we will only see the proof sketch for almost richness, which is a bit more involved. So what we have to show is that for every non-trivial partition there exists a corresponding distance function, such that if we give this distance function to our algorithm as input, we obtain the partition that we want. If we have a given partition that we call P, the distance function is constructed in this way that you can see in the right. If two objects belong to the same cluster, then we assign a distance of epsilon, while if they belong to different clusters, then we assign a distance of alpha, with alpha much greater than epsilon. Then the result of our composite evaluation matrix on P is 0 for the intracluster distance, and alpha minus epsilon, which is almost equal to alpha, since alpha was much bigger than epsilon, for the intercluster difference. And obviously this is optimal. So the first part of the almost richness axiom is proved. For the second condition, which requires us the fact that we use this construction. For every possible pair of instances, we use the same distance, call it epsilon. Then, by our definition of the composite quality criterion, for every possible partition, the quality metrics are both equal to 0. So all clusterings are non-dominated, and so they are optimal. And in this case, we have that the possible union over all possible distance functions and three-way clustering returned by the algorithm is the set of all partitions. And this ends our proof. Since this algorithm that we studied is okay, the result that we obtained is quite good because we proved that essentially in the case of three-way clustering, the no-free lunch theorem does not hold. We also wanted to study a more practical algorithm that is in fact used in application. And so we focused on studying three-way k-means, which is the most widely used three-way clustering algorithm. You can see the pseudocode for this algorithm, which is very similar to standard k-means, but we also have two thresholds based on which we decide whether placing the instances in the core regions or in the fringe regions. If the instances are normalized, as you can see on line 1, after all the requires instructions, then three-way k-means obviously satisfies scale invariance because in fact it is scale independent. However, three-way k-means does not satisfy consistency and almost richness. Almost richness is not satisfied almost obviously because the image of three-way k-means only contains all possible clusterings with exactly k clusters. So obviously almost richness does not hold. While the proof for consistency requires an example that you can see in the paper. While it does not satisfy almost richness, three-way k-means satisfies another interesting criteria, which is three-way k-richness. Basically, if we set k, then the image of three-way k-means contains all possible three-way clusterings with exactly k clusters. This is a very interesting property that encodes the fact that once we assume some inductive bias, namely the number of clusters equal to k, then restricted to that inductive bias, the three-way k-means algorithm is universal. So it is, at least in principle, it is able to recover all possible three-way k clusterings. The appropriate notion of consistency to characterize three-way k-means is much more technically involved. And it is directly based on the true thresholds that are used in the algorithms. Namely, we say that a clustering, that two distance functions, and so the corresponding clusterings are consistent with each other if the way in that they assign instances to the core and fringe regions does not change. And so the characterization that we give in this paper, in our paper, is that three-way k-means is exactly the algorithm that satisfies scale invariance, three-way k-richness, and this other definition of consistency that we call the small delta, big delta consistency. So, in conclusion, in this work we studied an axiomatic characterization of two different clustering algorithms. One is more theoretical in the sense that it was introduced to for a technical argument, and while it has a very high representational flexibility. It is very computational complex. The other is a very practical algorithm that is used in practice and which is not too much computational complex but has a very limited representational flexibility. An important thing to note is that three-way k-means is computationally efficient only if the centroids and the number of clusters are already fixed. Otherwise, the problem of finding appropriate centroids is NPR'd by itself. The problem of finding the most suitable value of k is also NPR'd, and if we get together all these two problems, then obviously we are still NPR'd, and probably also we are in exp time. So three-way k-means is computationally efficient, yes, if we make some kind of assumptions and we impose some kind of inductive bias. What are the open problems that we leave in our paper? First, one interesting aspect is that the characterization of three-way, the algorithm that we give in our proof of our main result is actually satisfies a stronger notion of richness. In fact, the image of the algorithm that we provided actually contains most three-way clusterings, but not all. So it will be interesting to characterize more precisely the class and the capacity of this algorithm. The second problem regards the fact that this same algorithm unfortunately has super exponential complexity. Otherwise, it would be the best and optimal three-way clustering algorithm. The question here is if it is possible to design randomized or approximation algorithms that obviously in the average case perform worse than the algorithm that we presented, but that can be used in practice. The third problem regards the fact that this type of characterization, while are interesting because they intuitively give us an idea of model capacity, of the representational capacity, of the representational power of different clustering paradigms, or of trade-offs between model capacity and the inductive bias, or computational complexity, they give no information about performance. So we know that at least in principle, the algorithm that we proposed is able to find an appropriate clustering, but we don't know if we give some specific dataset what we expect the results, for example, measured by accuracy or other metrics such as the Davis-Bouldin index of these algorithm are. These issues have been widely studied in the case of supervised learning, for example, through pack learning theory, and so it will be interesting to see if we can give some pack learning-like guarantees also in the case of three-way clustering. There are some results in this sense for hard clustering, but it is not so easy to, it is not so straightforward to generalize these results to the case of three-way clustering because the structure that we have is much more complex. So that ends my presentation. Thank you for your attention. And if you have any questions, I will be happy to answer them also via email. If you want, you can contact me at the address that you can see on the right. Thank you for your attention.